Hello, my name is Vanessa and I'm going to present the paper using IoT mesh network to extend wireless coverage in industrial environment. Our outline is made by introduction, IoT mesh deployment, experiment analysis, data transfer rate, throughput, delay and loss, final discussion, advantages, and future works. For our introduction, we know that the Internet 4.0 has given rise to the IoT, also known as the Industrial Internet of Things. This technology enables machines and devices to interact through wireless communication. However, it is essential for IoT services to have low energy consumption, minimal communication delay, and adequate throughput. Unfortunately, Zigbee IEEE 802.50.4 and BLE fall short of those requirements. Therefore, this paper focuses on analyzing data from the use of IoT mesh networks to improve wireless coverage in the industrial environment. Mesh networks allow direct communication between devices in a more dynamic network. This approach offers advantages in the industrial environment. For this purpose, we develop an IoT mesh solution to test a real case scenario to evaluate data transfer, throughput, delay, and loss depending on the number of hops in the mesh backbone. For our IoT mesh deployment, to further explain our solution, we concentrate on establishing an IoT mesh network using SPMDF Mesh Developer Framework by Espressive, primarily focusing on routing functionalities. We choose to use version 4.4.3 of SPMDF as it is compatible and stable with our testing devices. Additionally, we use the Arduino IDE and libraries with some adjustments to enable network connectivity so that the mesh network can transmit data beyond the internal network boundaries. For our experiment analysis, we downsized the IoT mesh to 3 ESP devices using the no-MCU chipset and our 2.4 connection with 3 decibels omnidirectional antennas. Each device had a distance of approximately 5 meters, with the nearest device to the access point being the root node and the others being nodes and leaves. The ESP can achieve a maximum rate of 15 megabits per second in AP mode, following the IEEE 802.11b standard. But the performance in mesh networks is unpredictable, so we decided to test the limit with mesh topology. To replicate the challenges of the industrial environment, the experiments took place in the Information Technology Department, the TIC, at the State University of Ceara, UECE. This was possible because the TIC contains various equipment such as servers and smartphones that can interfere with the wireless network signals. So we can simulate a real-world scenario, use 3 ESPs, 32S nodes, 1 client device, and 1 network router. For testing the transfer rate, we use the speed test tool. That is a tool for measuring download and upload speeds by exchanging data packages between users and servers, measuring the time to complete the round trip of these packages. We conducted 3 tests with the connection of the IoT mesh. In the first experiment, for the first test, we had the client connecting indirect access to the IoT mesh, achieving a download speed of 5.1 megabits per second and an upload speed of 2.3 megabits per second, suitable for uninterrupted 1080p video streaming. As we can see in this graph with the blue line. In the second test, the client had access to the IoT mesh with one network hop. He achieved a download speed of 3 megabits per second and an upload speed of 1.3 megabits per second. This represents a decrease of 42% in download and 44% in upload compared to the first test. As we can see here in the green lines of the graph. And in the last and third test, the client has access to the IoT mesh with 2 network hops. It achieved a download speed of 1.5 megabits and an upload speed of 4.6 megabits per second. This shows a 50% decrease in download and 54% in upload compared to the second test, and a decrease of 71% in download and 74% in upload speed compared to the first test. As we can see, this third test in the orange lines in the graph. For the second experiments, we use the iPerth tool to measure network performance. This technology is used to directly measure transfer rates between IoT mesh devices by accessing bandwidth and data transmission quality between network devices. This experiment demonstrates a decrease in throughput and in bandwidth as data travels through more hops in the mesh network. Well, our tests was like this. The first test, we use the root node and obtain a result of 4.4 megabytes transfer and 3.5 megabits per second of bandwidth. As we can see here in the graph represented by the blue line. In the second test, we use one hop and obtain a result of 2.18 megabytes transfer and 1.65 megabits per second bandwidth, indicating a 51% drop in throughput and 53% in bandwidth compared to the first test, as we can see here in the green lines in the graph. In the third test, we use 2 hops and obtain a result of 0.92 megabytes transfer and 0.66 megabits per second bandwidth, with a decrease of 68% in throughput and 6% in bandwidth compared to the second test, and a decrease of 80% in throughput and 82% in bandwidth compared to the first test, as we see represented here in the graph by the orange line. The delay and loss. We use the ping tool to analyze the reachability and responsiveness of the host www.uece.pr. This tool sends ICMP packages to the target services and records the travel time for each package, helping to measure network performance, troubleshoot problems, and detect packages loss and latency variation. The test was conducted with packages of varied size, 100, 500, and 1,000 bytes for a detailed analysis. In case A, with packages for 100 bytes, we obtain a latency of 61 milliseconds in test 1, 113 milliseconds in test 2, and 200 milliseconds in test 3 with no data loss in any of these tests. For the case B, with the ping up of 500 bytes, we obtain a latency of 67 milliseconds in the first test, 97 milliseconds in the second test, and 200 milliseconds in the third test, again with no data loss in any of the tests. And for the last case, with 1,000 bytes, we obtain the latency of 82 milliseconds in test 1, 109 milliseconds in test 2, and 133 milliseconds in test 3, also with no data loss. Comparing the cases, we notice that when we ping at 1,000 bytes, the latency is smaller than when we ping smaller values like 100 or 500 bytes. For our final discussion, we have our results that shows that there is a variability in packet transmission through different nodes in the mesh network topology. Additionally, packet size can affect latency, resulting in network heterogeneity and transmission anomalies. Nevertheless, the network provides robust connectivity for numerous devices and sensors with data transfer rates suitable for 720p YouTube videos, facilitating complex sensory and monitoring tasks and no package loss. The advantages, we have another approach for IoT in Wi-Fi IEEE 802.11 presenting advantages like plug and play capacity, scalability, low cost, and others. And as industrial facilities have complex layouts, the network signal may face obstacles that can cause dead zones and coverage gaps, resulting in poor connection and reduced data throughput. For future work, this paper can be used to address the challenges with Wi-Fi in terms of throughput, latency, and signals coverage. It can also involve accessing the IoT mesh network in different industrial environments and experiments with various tools. Besides that, it can be used with more mesh nodes, different types of mesh topologies and energy sources, and also to observe the behavior of the network during failures. Now here's our team that is made up by Carlos, Aquino, Moura Braga, Yanne Oliveira, Evellin, Moura, Vanessa Carvalho, which is me, and our professor Rafal Lopes. And here is our contact information, our email, our Instagram, and our app's website. Thank you for your attention.